Hey everyone, this is Amar Babu Kolluri. Today I am presenting and making video on my AI project called Netflix title clustering using unsupervised learning. Here I want to talk a bit about unsupervised learning. The unsupervised learning is a type of machine learning where the model learns patterns and structures from data without labeled answers. In simple explanation, you give the computer raw data with no correct output or label. The computer tries to find patterns, group similar things, and reduce the data size. In instance, if we feed a machine a lot of pictures, like if suppose if we take animals, it doesn't tell us what each animal is. Like it might group all the animals like dogs together, cats together, elephants together, etc. based on visual similarities. That's how unsupervised works. Coming into my project introduction, what is the challenge and why it matters? Like the challenge I focused on is that Netflix has thousands of titles and users often struggle to discover new content they might like. While Netflix does have a recommendation system, it depends on user behavior like watch history or ratings. That creates a problem for new users or new content that has no viewing data. So I explored a different approach. Can we group similar Netflix titles based only on their content, like descriptions, genres, or country, without needing user activity? And this matters because such clustering could help build smarter search systems, better browsing tools, or even be used in other recommendation engines that are more content aware. And go. This slide talks about the data set. Where did I get the data set? Like what's the source and everything for this project? I used the Netflix movies and TV shows data set from Kaggle. It contains metadata about more than 8,000 titles, including movies and TV shows available on Netflix until the year 2021. There are 12 columns in the data set, and each row represents one title. One represents some of the columns included, like title. It tells the name of the show or movie, type, whether it's a TV show or a movie, description, a short summary or a synopsis of the content, and the additional context like directors, cast, movie genre, release date, release year, and their ratings, etc. Uh, After coming to the pre-processing, I pre-process the text by removing punctuations, lowering case, everything, removing stop words, and then converting the descriptions into numerical vectors using the TF-IDF vectorization. And yeah, from the topic 3, the method and the model for this project was I used a step-by-step pipeline that includes data pre-processing, feature extraction, clustering, and dimensionality reduction for visualization. First, I cleaned the description text. I removed punctuations, lowercase, all words, and removed uh, common stop words like the, end, of, etc. And this is my output from my data underscore clean.py. This is my sample output that I got from my code. This is my step to pipeline from method and models. A clean text data was converted into numerical form using TF-IDF, which stands for term frequency inverse document frequency. The TF-IDF emphasizes words that are unique to a description, reducing the weight of words that appear frequently across all entries. A maximum of 5,000 features were used to balance between modal richness and computational efficiency. And this is the sample output I got from the code. The TDF ID of matrix shape in between 8,807 to 5,000 important words. Coming into step 3, the clustering algorithms, we use two main clustering algorithms. Those are k-means and dbScan. Here the k-means is a widely used algorithm that partitions the data set into k clusters. I set k equals to 10 based on initial experimentation. Every title was assigned to a cluster. K-means is efficient and accurate and performs well when clusters are roughly spherical and evenly sized. And this is my sample output that I got from the code that I did. The other clustering algorithm called dbScan. The dbScan is a density-based algorithm that group titles that are close to each other and marks sparse points as outliers. This model doesn't need the number of clusters to be predefined. It is particularly effective at finding arbitrary shaped clusters and is excellent for detecting noises. And this is my sample output of dbScan clustering. Diving into step 4, the dimensionality reduction, there are two main methods we used. The PCA stands for Principal Component Analysis. This is a linear technique that reduces dimensionality while preserving variance, useful for fast overviews. And the other one, TSNE, which stands for Distributed Stochastic Neighbor Embedding, which is a non-linear method that better preserves a local structure. It creates clearer 2D cluster visualizations. These two models produced new datasets with added cluster labels and allowed visual inspection using 2D scatter plots. Diving into deep evaluation of clustering, the results what we got and the analysis of clustering here. The k-means, which is the TSNE visualization of k-means, revealed that several clusters formed well-defined groups. There were a few overlaps, but generally the clustering was meaningful. The Silhouette score, a metric that measures how similar an item is to its own cluster compared to other clusters, was moderate, suggesting reasonable cluster separation. And the dbScan, in contrast, dbScan produced one dominant cluster, several niche clusters, and a large number of outliers. This is expected as dbScan does not force every item into a cluster. The outliers can be interpreted as unique shows that do not share themes with the rest of the content. The Silhouette score was lower, but this does not necessarily indicate failure. Rather, it reflects dbScan's conservative approach to grouping. Visually, the TSNE plots helped confirm that dbScan was effective at isolating noise and tight content groupings. PCA was useful for initial inspection, but TSNE provided better cluster and clarity. Yeah, there are the analysis of visualization summary here. There are three scatter plots. We got the PCA one and the TSNE, better for true cluster shape and outliers visible in DBScan TSNE plots. And we go. This is the K-means PCA scatter. This scatter plot shows the result of K-means clustering reduced to 2D using PCA. You can see 10 different clusters, each representing by color. While there is some overlap, the plot shows a general grouping pattern that PCA gives you a fast overview, but it flattens some of the true structure. And this plot represents the K-means clustering TSNE reduction. This plot also shows K-means clusters, but now using TSNE for dimensionality reduction. TSNE better preserves the shape of the data, and you can see tighter, more natural cluster formations. There is still some mixing, but this view shows the several clusters are compact and meaningful. In the TSNE, this plot gives you a more accurate visual of cluster shapes and closeness compared to PCA. Here we see the results of DBScan clustering also visualized using TSNE. The large blue area represents this labeled as outliers. The clustering starts from -1. The smaller colored groups show tight clusters of similar content, and DBScan did a great job of identifying shows that don't fit into any groups. This DBScan plot is effective for spotting outliers, outlier titles, and uncovering niche context clusters. And this is our last conclusion and some takeaways for our project. That this project successfully demonstrated that Netflix titles can be meaningfully grouped using their descriptions alone, without relying on any user history or ratings. It is possible to reveal a natural structure within the content using TF, IDF, and clustering algorithms like K-means and DBScan. K-means was effective at producing general balanced clusters. DBScan was better at identifying niche groups and flagging outliers, making it useful for exploratory tools or detecting unique content. Dimensionality reduction techniques like TSNE greatly enhanced interpretability. And through this project, through this final project, I gained a deeper understanding of natural language processing techniques like tokenization and stop word removals. I also learned how to extract meaningful features using TF-IDF vectorizations and explored the differences between partition-based methods like K-means and density-based methods like DBScan. I realized how important visualization is in unsupervised learning, not just for understanding clusters, but also for explaining results to others. Overall, this project showed me how unsupervised learning can power content recommendation systems even without user data, which is especially useful in cold start scenarios. And this is my overall presentation about my project. And thanks for giving me this opportunity in this summer. Thank you for a great semester. I really enjoyed your class and learned a lot about AI and its real world applications. AI is truly becoming a vital part of our daily lives, and your teaching helped me understand its depth and relevance. And thanks again for your guidance and support throughout the semester. Wish you a restful and enjoyable summer. Thank you. Thank you so much.